Right now, in whatever room you happen to be resting in, something is quietly leaving your body. Not light, not sound, but warmth, drifting out from your skin in a thin, invisible current, moving from the heat of you into the slightly cooler air and into anything your body happens to be touching. You don't see it go, you don't hear it go, but if your fingertips are resting against a surface nearby, that warmth is being pulled away at this very moment, and the rate at which it leaves depends entirely on what your skin has decided, without asking your permission, to touch. This is where our story begins tonight, with a small and old and endlessly interesting confusion, one that almost everybody has felt, but almost nobody has paused to untangle. Imagine a room, any room, perhaps one you know well, a room that has been sitting quietly for hours, undisturbed, its air settling into a single, even temperature. Nothing in that room is being heated or cooled on purpose. No radiator clicks on, no draft slips under the door. Given enough hours of stillness, everything inside that room, the walls, the floor, the furniture, the doorknob, the windowsill, all of it drifts toward the same temperature as the air around it. This is simply what happens when things are left alone long enough. Heat doesn't play favorites. It moves from warmer places to cooler places until there's no difference left to move, and then it stops, or at least it slows, to something so faint we could call it stillness. So let's say this room has reached that quiet equilibrium. Let's say, for the sake of a gentle experiment, that everything in it, truly everything, has settled at exactly the same 18 degrees. The wooden table by the window, the metal leg of a lamp beside it, a stone tile near the doorway, a cotton blanket folded on a chair, all 18 degrees, all patient, all unmoving, all having given up whatever heat they needed to give up, or absorbed whatever heat they needed to absorb, until they matched their surroundings exactly. If you had a very precise thermometer, and you touched its little sensor to each of these surfaces in turn, it would tell you the same number, over and over. Table, lamp, tile, blanket, table again, just to check. 18 degrees, 18 degrees, 18 degrees. No surprises, no disagreement among the objects. They are, by any careful measurement, in perfect thermal agreement with one another. And yet, if you were to walk into that very room, sleepy and barefoot, and rest one hand on the wooden table, and then move it to the metal lamp, something strange would happen inside your own perception, something that seems to quietly defy what the thermometer just told you. The wood would feel, more or less, like nothing at all, mild, neutral, almost the same temperature as your own skin, maybe just a touch cooler, easy to ignore, but the metal would feel different, sharply different. A small, cool jolt would travel up through your fingertips, a sensation your brain would very quickly and very confidently label as cold, even though, and this is the strange part, even though the thermometer insists the metal is exactly, precisely, unmistakably the same temperature as the wood you touched a moment before. This is not a trick of the mind, not exactly, though it does live inside the mind in an important way. It's not that your senses are lying to you, it's that your senses are telling you something true, just not the thing you assumed they were telling you. And that gap, between what we assume our fingertips are measuring and what they are actually measuring, is the heart of tonight's puzzle. Because here is the quiet, almost embarrassing truth hiding underneath this whole experience. Your hand has never once, in your entire life, been able to directly sense temperature. Not really.
not in the way we casually think it does. What your skin actually senses, what its nerve endings are built to detect, is the flow of heat, the movement, the rate at which warmth is leaving your body, or in rarer cases, arriving into it. Your fingertip doesn't have some built-in thermometer, quietly reading off numbers like 18 degrees, 19 degrees, and reporting them faithfully to your brain. Instead, it has something more like a current detector, a patch of living tissue, exquisitely sensitive to how quickly its own warmth is escaping into whatever it happens to be touching. When that escape is fast, the nerves fire in a pattern your brain interprets as cold. When that escape is slow, the nerves stay relatively quiet, and your brain interprets that quiet as something closer to warm, or at least as nothing worth alarming you about.
So when you touched the wood, warmth did leave your fingertip, because your fingertip, at something close to 32 or 33 degrees, was indeed warmer than that 18-degree surface. Heat obediently began flowing outward, from you into the wood, exactly as physics demands. But it flowed slowly, gently, almost politely, if a physical process can be called polite. And so your nerves, sensing only a mild trickle of heat leaving, sent back a mild, unremarkable signal. Nothing to see here, they seemed to say. Carry on. But when you touched the metal, heat left your fingertip at a dramatically faster pace. The same starting temperature in your skin, the same starting temperature in the object, and yet a completely different rate of departure. A flood instead of a trickle. And your nerves, which are built to notice rate rather than absolute number, responded accordingly, with urgency, with a signal your brain translates instantly and instinctively into the word cold, even before you've had a chance to think about it consciously. It's a little like standing at the edge of two rivers that both happen to be, let's say, exactly 1 meter deep, identical depth if you measured it with a ruler, but one river is nearly still, its surface barely moving, while the other is rushing past with real force, real current, pulling at anything that enters it. If you stepped into each one, you would not describe them as the same experience, even though depth, the one number you happen to measure, is identical. Your body would feel the difference in flow, in force, in how much of itself was being carried away by the current, long before your mind got around to comparing their depths on paper. Heat, leaving your skin, behaves a little like that. Same starting depth, so to speak, very different currents. This is worth sitting with for a moment, letting it settle the way warmth settles through a quiet room. Temperature, the number a thermometer gives you, describes a state. It's a snapshot, a single frozen fact about how much thermal energy is packed into something at one instant. But what your hand experiences isn't a snapshot. It's a process, a rate, a verb, rather than a noun. Your hand is not asking what temperature is this, even though that's the question we assume we're asking when we reach out to touch something. Your hand is really asking, how quickly is my warmth leaving me right now, through this particular surface? And your brain, without ever pausing to explain its logic, quietly translates the answer into the comfortable shorthand of hot and cold. Which means that two objects can share a temperature completely and honestly, agreeing with each other down to the decimal point, and still feel like strangers to each other under your palm. The room was never lying. The thermometer was never wrong. It's simply that temperature and the feeling we call temperature are not quite the same thing, however seamlessly we've spent our whole lives treating them as if they were. There is the room's honest, physical reality. 18 degrees is 18 degrees is 18 degrees, and then there is your skin's translation of that reality into something felt, something that depends not just on how much heat is present, but on how easily, how quickly, how willingly it can travel out of you and into whatever you happen to be resting your hand upon. So the puzzle we're settling into tonight isn't really about metal, and it isn't really about wood.
Not yet. It's about this quieter, stranger fact sitting underneath both of them, the fact that your body has been measuring flow all along and calling it temperature, and has done so smoothly, so automatically, across every doorknob and windowsill and stone floor you've ever touched in your life, that you never had reason to notice the difference. And once you do notice it, once you let that small shift settle in, the next question arrives almost on its own, gentle and curious rather than urgent. What is it, exactly, about a material, about its hidden inner structure, that lets heat rush through it quickly in one case and amble through it slowly in another? That's where we'll wander next, softly, into the quiet architecture of materials themselves.
Let's slow down and sit with three words we've been using almost interchangeably for our entire lives: temperature, heat, and cold, because tonight it will help to gently pry them apart and look at each one on its own, the way you might take apart an old clock, not because it's broken, but because you want to understand why it has always kept such good time. Temperature, in the strict and careful sense that physicists came to over a couple of centuries of patient argument, is a measure of something happening at the scale of atoms and molecules, a measure of how vigorously the tiny particles that make up a substance are jittering and vibrating, and, in the case of gases, zipping around and colliding with one another. A hot object isn't hot because it contains some separate glowing substance called heat, though for a long time many serious thinkers believed something close to that, imagining heat as an invisible fluid, weightless and self-repelling, that flowed from warmer bodies into cooler ones. That fluid even had a name: caloric, and it was a perfectly respectable scientific idea for a good while, useful enough to make correct predictions in many situations, wrong enough underneath that it eventually had to be let go. What was actually happening, we now understand, was never a substance moving, so much as motion itself moving, jostling passed along from one particle to its neighbor like a shiver traveling down a rope. Temperature, then, is essentially an average, a way of describing how much that jostling amounts to across countless trillions of particles, too many to ever count individually, so we settle for a kind of statistical portrait instead, a number that tells us the general busyness of a material without needing to know what any single atom happens to be doing at any given instant. Thermal energy is a close relative of temperature, but not quite the same thing, and the difference between them is worth sitting with for a moment because it explains a great deal that would otherwise seem contradictory. Thermal energy is the total amount of that jostling motion contained in an object, added up across every particle inside it, which means it depends not only on temperature, but also on how much material there is and what that material happens to be made of. A large lake in early spring and a cup of tea might, in principle, share the same temperature, both hovering somewhere near lukewarm, and yet the lake contains an almost unimaginably larger reservoir of thermal energy simply because it contains so much more matter, so much more water, for that gentle jostling to be spread across. This is why a lake takes the whole of spring to warm and the whole of autumn to cool, while your tea can swing from scalding to cold within the span of a single, unhurried conversation. Temperature tells you the intensity of the motion, so to speak, while thermal energy tells you its sum total, and these can move independently of one another in ways that feel almost paradoxical until you've had a chance to think them through slowly, without pressure, the way we're doing right now.
And then there is cold, which turns out to be the strangest of the three, because cold, in the language of physics, doesn't really exist as its own thing at all. There's no cold energy waiting somewhere to rush into a warm object, the way caloric was once imagined to rush the other direction. Cold is simply the experience, the felt sensation, of heat leaving you, or of heat failing to arrive when you expected it to. When you press your palm against a chilled window on a winter morning, nothing cold is entering your hand, no icy essence seeping in through your skin. Instead, your own warmth, the very same jostling motion that's been quietly keeping your palm at its usual gentle simmer of a temperature, is being pulled out of you, drawn through the glass, spreading into the vast cool air on the other side. What you're calling cold is really the sensation of loss, the felt experience of your own warmth departing faster than your body is comfortable losing it, and your nerves, which were never built to measure temperature directly, are wonderfully well built to measure exactly this, the rate at which something is slipping away. This is worth pausing on, because it reorganizes something we usually take for granted. Your skin does not contain thermometers in the way your bathroom cabinet might contain one, a device calibrated to read out a number regardless of context, regardless of what it happens to be touching. What your skin contains instead are thousands of small nerve endings exquisitely sensitive to the movement of heat, some tuned to notice warming, others tuned to notice cooling, and both kinds are really reporting on flow, on change, on the direction and speed of energy crossing the boundary between you and the world. A true thermometer doesn't care how it reaches its reading, whether the mercury climbs quickly or slowly, whether the material around it conducts well or poorly. In the end, it settles at the actual temperature of its surroundings and simply reports that number, patient and indifferent to the journey. Your hand cares enormously about the journey. Your hand's whole report is the journey. It tells you not what temperature something is, but how urgently your own warmth is being pulled toward it. And those two things, while related, are simply not identical, and confusing them is the most natural mistake in the world, one that essentially everyone makes without ever noticing they've made it, because the confusion costs us nothing in daily life. We don't need to know the precise physics of heat flow to decide whether to put on a sweater. Think for a moment about stepping out of a warm bath into ordinary room air that a thermometer would describe as perfectly mild, perhaps 22 or 23 degrees, nothing dramatic at all. And yet that same mild air, brushing against skin, that has just spent 20 minutes adjusting itself to bathwater warmth, can feel astonishingly brisk, almost unkind, for the first several seconds. Nothing about the room changed. No draft crept in, no window was left open. What changed was the rate at which your skin was suddenly losing warmth, because your skin had recalibrated itself, quietly, and without your permission, to the temperature of the bath, and the sudden gap between that expectation and the cooler air produced a rush of heat, leaving you far faster than it had been leaving moments before. Your nerves reported that rush faithfully, and your mind, receiving the report, reached for the only vocabulary it had on hand, and called it cold, even though by any honest thermometer's account, the room was mild, was pleasant, was exactly what it had been the whole time you were bathing. This is also, incidentally, why a single object can feel different temperatures to different parts of your own body at the very same moment, which is a small, everyday miracle we rarely stop to marvel at. Step from a tiled bathroom floor onto a bath mat and then back onto the tile, and each transition announces itself clearly, tile feeling cooler, mat feeling warmer, though we might reasonably assume, given that they've been sitting in the same room all night, that they share very nearly the same temperature, warmed or cooled together by the same surrounding air, hour after hour, with no reason for one to have drifted meaningfully from the other. What differs between them isn't how much warmth they contain, or even, in any large sense, how warm they are. What differs is how eagerly each one accepts the warmth leaving your foot, how quickly each can absorb it and carry it away into itself and the floor beneath. And it's this eagerness, this rate of acceptance, that your soul is truly reporting when it makes its quiet, wordless judgment between the two.
We're circling, gently and without any need to rush, toward the actual heart of tonight's puzzle, the metal and the wood themselves, sitting perhaps side by side on the very same tabletop, warmed or cooled by the very same room for the very same number of patient, unhurried hours. But before we let them meet under your hand, it's worth carrying forward this quieter understanding we've just built together, that what your palm is about to report is never simply their temperature, honest and equal as that temperature may be, but rather how differently each of them is built, deep down in its hidden structure, to accept and carry away the warmth your body has been offering, without asking, since the moment you were born. Let's go smaller now, smaller than tabletops and bath mats and even the whorls of skin on your fingertip, down to a scale where the word touch starts to mean something almost embarrassingly literal. Because when your palm finally does rest against the metal, what happens there is not some abstract exchange of an invisible fluid called heat, sliding obediently from one surface to another like water finding a drain. What happens is collision, actual, physical, ceaseless collision, though of a kind so small and so fast that no instrument built by human hands has ever let us watch a single one happen, only infer, from its aftermath, that billions of them must be occurring in the space of a heartbeat. Every material you have ever touched, however still it appeared, however solid and settled and finished with movement it seemed to be, is in fact a restless crowd of atoms, and those atoms are never truly at rest. Even in something as cold as an ice cube, even in something as calm as a stone that has sat in a garden for 100 years, the atoms are vibrating, trembling in place, held to their neighbors by bonds that act rather like tiny springs, pulling them back whenever they wander too far, letting them snap back out again a moment later. This is simply what warmth is, at the level where physics stops using comfortable words like warmth at all. Warmth, at that depth, is motion. It is the vigor, the sheer trembling energy with which those atoms are jittering against the springs that hold them in their places. A warmer object is not an object with more of some invisible substance poured into it. A warmer object is an object whose atoms happen, on average, to be shaking more energetically than the atoms of a cooler one nearby. Your own skin, of course, is made of atoms doing exactly the same kind of trembling, and at the moment your palm settles against the metal, something almost absurdly simple takes place at the boundary between the two. The atoms of your skin, jittering along at the brisk and busy pace that a living, blood-warmed body maintains, come into contact with the atoms of the metal's surface, which happen, in this ordinary room, to be jittering rather less energetically than yours. Not because the metal is unusually cold, we've already spent our time establishing,
that it very likely isn't, but simply because that is the pace its atoms have settled into after a long, quiet night in that particular room. And when a faster jittering atom bumps against a slower jittering one, again and again, thousands upon thousands of times in the first fraction of a second of contact, something happens that will feel entirely familiar to anyone who has ever watched two dance partners of very different energy try to match steps. The livelier one doesn't instantly calm the other down to stillness, and the calmer one doesn't instantly leap up to match the livelier one's pace. Instead, through sheer repeated bumping, through friction and jostling, and the transfer of tiny amounts of motion from one to the other, they begin, very gradually, to average out. The fast atom slows, ever so slightly, with each collision. The slow atom quickens, ever so slightly, in return. Multiply this by the staggering number of atoms lined up along even the smallest patch of contact between your palm and the metal, and you begin to see what your nerve endings are actually detecting, not cold arriving. Warmth departing, atom by atom, collision by collision, carried away from your skin and dispersed into the vast, cooperative, energetic swarm of the metal itself. Now here is where metal begins to reveal the particular trick that makes it metal, the thing that separates it so sharply from wood, or cloth, or plastic, in this business of collecting warmth from a hand. Inside a solid, ordinary material, this passing along of motion generally has to travel the slow way, atom nudging its immediate neighbor, which nudges its immediate neighbor in turn, a bit like a message passed by tapping the shoulder of the person standing directly beside you, who taps the shoulder of the next person, and so on down a long and patient line. It works, but it works at the pace of that particular kind of relay, no faster than each individual handoff allows. Metal, though, has an extra set of messengers available to it, a population of electrons that are not bound tightly to any single atom at all, but instead drift rather freely throughout the entire structure, the way a light fog might drift through a forest rather than clinging to any one tree. Physicists and chemists sometimes describe this loose population, only half in jest, as an electron sea, and it is a genuinely useful image to hold on to as you drift toward sleep tonight. A great shimmering sea of tiny charged particles, filling the spaces between the fixed and orderly atoms of the metal, able to move, able to carry energy along with them, far more quickly and far more freely than any single vibrating atom passing its motion to the next. This same free-roaming population of electrons, incidentally, is exactly what makes metals such capable conductors of electricity as well, which is not a coincidence tacked on for tidiness, but the very same underlying property, doing two different jobs at once, one of the small, quiet elegances that turns up now and then in the natural world if you happen to be paying attention at the right depth. Copper wiring carries a current, for the same essential reason a copper doorknob carries warmth away from your hand so briskly, because in both cases, there is a crowd of nearly unbound electrons, ready and able to move, to jostle, to relay motion and charge alike across the material, at a pace the more rigid lattice of atoms alone could never achieve on its own. So when the energetic atoms of your palm begin knocking their motion into the outermost atoms of the metal, that motion doesn't have to wait patiently for a slow relay down through fixed positions in a crystal lattice. It gets picked up almost immediately by this drifting sea of electrons, which then goes rushing off into the depths of the object, spreading the received energy through the whole mass of the metal with startling efficiency, the way a drop of ink might vanish almost instantly into a large, gently stirred glass of water, rather than sitting as a visible bead on the surface of something still. The warmth your hand offers up doesn't accumulate at the point of contact, doesn't linger there, even for a moment, to let your nerve endings catch their breath. It is whisked away, distributed, shared out across a vast electron-rich interior, almost as fast as it arrives, which means the surface directly under your palm never has the chance to warm up to match you. It stays perpetually a little behind, perpetually eager for more, and your nerves, sensing this ceaseless and remarkably efficient departure, report it in the only honest language they have, which is the sensation of something cold. Wood tells an entirely different story, not because its atoms are behaving differently in principle. They still jitter, they still collide, they still pass motion along in essentially the same fundamental way, but because wood simply lacks that free-flowing sea of electrons to carry the energy off with any speed. Wood grew, once, as a living thing, layer upon layer of cellulose fiber, built up slowly across seasons, and it carries within its structure something that turns out to matter enormously here, an abundance of tiny enclosed pockets, cavities that once served as channels for water and nutrients in a living tree, and now sit largely full of ordinary air. Air, as it happens, is one of the worst materials imaginable for relaying vibrational motion from one atom to the next, its molecules spaced so far apart, relatively speaking, that collisions between them are comparatively rare, and their capacity to carry energy onward is correspondingly feeble.
So the warmth your palm hands over to the surface of the wood finds itself, almost immediately, funneled into a structure riddled with these small stalling pockets of nearly stagnant air, each one acting like a tiny obstacle in what would otherwise be a smooth and rapid relay. The motion has to work its way around them, through the solid fibers, rather than across the gaps, taking a slower, more winding path than it would through the tightly packed, electron-assisted interior of a metal. The consequence of this slower internal pathway is that the wood surface, right where it meets your hand, warms up almost as quickly as your hand is giving warmth away, because the energy arriving there has nowhere fast to go, no eager electron sea waiting to whisk it off into the depths. It pools, gently, right at the point of contact, the way heat pools in the top few inches of a still pond on a warm afternoon rather than spreading evenly through the icy water lying beneath. Within moments, the wood directly under your palm has drifted close enough to your own skin's temperature that the collisions occurring there begin to even out, fewer atoms handing off motion in one net direction than the other, and your nerves, no longer registering any brisk and continuous departure, quiet down and report something closer to neutrality, something you're inclined to call merely cool, or sometimes not cool at all. We'll want to slow down for a while longer on exactly what your nerves are doing when they file these reports, because it turns out the skin itself has its own particular way of misreading a perfectly honest situation, and that misreading deserves its own unhurried unraveling before we let this evening's puzzle come fully to rest. Let's set the earlier picture aside for a moment, not because it was wrong, but because it deserves a companion, a set of actual numbers to lean against, so the feeling of coldness stops being just a vivid impression and starts being something you can, in a drowsy sort of way, almost calculate. Physicists and engineers have a term for how eagerly a material passes heat along, and they call it thermal conductivity, usually written with the lowercase letter k, and measured in units that describe how many watts of energy flow through a slab of the material 1 meter thick, across an area of 1 square meter, for every degree of temperature difference pushing that flow along. It sounds technical, and it is, but you don't need to hold on to the units themselves, only the general shape of the idea, which is that K is simply a number telling you how good a conveyor belt a substance makes for jostling atomic motion. High numbers mean an eager, efficient belt. Low numbers mean a sluggish, halting one, prone to backing up at every junction. Silver sits near the top of this list among common materials, with a conductivity hovering somewhere around 400 units on the standard scale. Copper trails not far behind it, somewhere in the high 300s, which is part of why old kitchens, the good ones, the ones with a wall of hanging pans that cooks were proud of, favored copper bottoms for cookware, since a copper base spreads a burner's heat evenly across a pan instead of leaving one blistering hot spot in the center, surrounded by cooler, sulking metal. Aluminum comes in lower still, somewhere near 200, which is why the disposable aluminum trays sold in supermarkets do a perfectly serviceable job at carrying heat from an oven into a casserole, even if a professional kitchen might reach for copper when precision matters more than economy. Iron and the various steels drift lower again, down into the 60s or 50s, softened by the particular arrangement of their crystal lattices and by whatever alloying elements happen to be mixed in, since even a small quantity of carbon or chromium threaded through the iron can measurably slow the electron traffic passing through it. And then, dropping almost off the bottom of any chart that includes metals at all, come the woods. Pine, oak, cedar, whatever species happens to make up your nightstand or your windowsill, cluster down around 1/10 of 1 unit, sometimes less, a conductivity so small that setting it beside copper's number feels almost like a typographical error, as though a decimal point slipped somewhere in the printing. It hasn't slipped. Wood genuinely conducts heat somewhere in the neighborhood of 2,000 times more reluctantly than silver does, and that factor of 2,000 is not a poetic exaggeration meant to make a bedtime story more dramatic. It is closer to the actual measured ratio, verified in laboratories with thermocouples and heated plates, and a great deal of patient, unglamorous repetition by people whose names rarely make it into any history read for pleasure. It's worth pausing on one of those names anyway, because the story of measuring conductivity carefully is older than you might guess. In the very early 1800s, a French mathematician named Jean-Baptiste Joseph Fourier became fascinated, almost to the point of obsession, with the way heat moved through solid bodies, and he built an entire mathematical framework, still taught essentially unchanged today, to describe that movement as a smooth, continuous flow, governed by simple, elegant equations. Fourier worked during a period when the study of heat was still tangled up with older, mistaken ideas about a weightless heat fluid called caloric, supposed to seep from hot bodies into cold ones, the way water seeps downhill, and though that particular fluid turned out not to exist, Fourier's equations describing the flow itself held up remarkably well regardless, because the mathematics of a gradual, gradient-driven spreading turns out to work whether you imagine tiny invisible fluid particles moving, or, as we now understand it, atoms jostling their neighbors through direct collision, and, in metals, through a rushing tide of shared electrons. It's a pleasant kind of accident in the history of science, a correct answer arrived at from a picture we now know to be incomplete, and it is one of many reminders that a useful equation can outlive the story originally told to justify it.
What Fourier's work eventually allowed later researchers to do, once instruments grew precise enough, was measure this conductivity value for material after material with real confidence, comparing a rod of copper against a rod of glass against a plank of oak, all heated identically at one end and monitored along their length, watching how quickly warmth crept from the heated tip toward the cooler far side. The metals, unsurprisingly by then, raced ahead. The woods and glasses crawled. Now here is the part worth turning over slowly in your mind before sleep pulls you under entirely, because it's the part that resolves the apparent contradiction sitting at the center of tonight's whole subject. None of these numbers, not Silver's 400, not Wood's tenth of a unit, describe temperature at all. They described rate. A block of aluminum sitting on a shelf in a cold room and a block of pine sitting right beside it will, given enough time to settle, arrive at exactly the same temperature as that room, no warmer, no cooler, both perfectly obedient to the basic rule that objects left alone eventually match the temperature of their surroundings.
If you left a thermometer resting against each of them for an hour, it would report identical readings, down to the fraction of a degree, assuming both objects had truly finished settling. The aluminum is not secretly colder. It has no reservoir of extra chill tucked away inside it, no special affinity for cold weather that the pine somehow lacks. What differs between them, and differs enormously, is only how quickly each one is willing to accept heat pouring in from your hand, or equivalently, how quickly each one drains that heat away from the warm surface of your skin once contact is made. Your hand, meanwhile, sits at a temperature the two materials both find equally cold relative to itself, somewhere near 98 degrees on the Fahrenheit scale your body prefers to maintain, sometimes a degree or two lower, right at the surface of the palm, depending on circulation and the temperature of the room you're sitting in. That gap between your palm's warmth and the shelf temperature of the metal or the wood is the driving force behind any heat flow at all, the gradient Fourier's equations depend upon, and that gap starts out identical for both materials. What happens next depends entirely on how efficiently each one can exploit it. The metal, with its ready electron sea, seizes that gradient eagerly and starts hauling energy away from your skin at a brisk, sustained pace, one that barely slows even as a few seconds pass, because the metal's interior is so good at redistributing the arriving heat throughout its whole mass that the surface in contact with you never gets the chance to warm up appreciably, never approaches your hand's own temperature, and so it keeps demanding more. The wood, lacking that internal redistribution system, accepts heat far more grudgingly, and the small quantity it does accept has nowhere fast to go, so the wood's own contact surface warms rapidly toward your skin's temperature, and the flow slackens almost as soon as it begins, the gradient itself shrinking because one side of it, the wood's surface, keeps creeping upward to meet the other. So the two blocks start this experiment at the same temperature and remain, throughout, entirely ordinary in that respect, obedient to every law of thermal equilibrium anyone has ever measured. What separates the sensation they produce is a question of speed and persistence in the transfer, not a question of stored coldness, and that distinction, subtle as it sounds while your eyes are growing heavy, turns out to be the entire resolution to the puzzle that likely got you wondering about any of this in the first place. There's still more to say about what happens on your side of that contact, in the skin itself,
Because your nerves aren't measuring temperature directly at all, not in the way a thermometer does, and the particular thing they are measuring instead is where this story quietly turns next.
Let's stay with that question for a while, because it turns out your nerves are not quite the simple thermometers we tend to imagine them to be. But before we follow them inward, there's a piece of the outward story still worth settling, a piece that often gets smudged together with conductivity as though it were the same idea wearing a different name. It isn't. And separating them apart, slowly, is worth the effort, because the smudging is exactly what leaves so many people lying awake, mildly puzzled, running a hand across a nightstand and a headboard, and not quite able to say why the difference feels so immediate. Conductivity, the property we've been leaning on so far, describes how willingly a material passes heat along once that heat is already inside it, from one interior point to the next, the way a bucket brigade passes water hand to hand down a line of firefighters. A metal's electron C makes it a marvelous bucket brigade, quick and tireless. Wood, full of trapped air pockets in its cellular structure, makes for a slow, hesitant one, buckets passed reluctantly, some water sloshing out along the way. That much we've covered. But there is a separate question, easy to overlook, about how quickly heat gets absorbed at the surface in the first place, at the very instant of contact, before there is any interior to speak of yet. And that question depends on more than conductivity alone. It depends on a property called thermal effusivity, a word that even many people who studied physics never happened to encounter, tucked away as it is in the corners of heat transfer textbooks rather than the opening chapters. Effusivity is, in a sense, a measure of a material's appetite for heat at the moment of first touch, and it isn't determined by conductivity by itself, but by conductivity working in partnership with two other properties, density and specific heat capacity, multiplied together and then square-rooted, though you needn't hold on to the arithmetic to follow the idea. Density is simply how much mass is packed into a given volume, how heavy a block feels for its size. Specific heat capacity is something a little more subtle, a measure of how much energy a material can absorb before its own temperature rises by even 1 degree, a kind of thermal patience, or perhaps thermal stubbornness, that varies enormously from substance to substance. Water, famously, has an unusually high heat capacity, which is part of why oceans warm and cool so slowly, compared to deserts, and metals, as it happens, tend to have comparatively low heat capacities, meaning it doesn't take much incoming energy to nudge their temperature upward. Effusivity bundles these three properties, conductivity, density, and heat capacity, into a single number that predicts something very specific, namely, what temperature two objects settle at, right at their shared boundary, the instant they touch. Not the temperature either one started at, not the temperature they'll eventually reach given enough time, but the temperature of that thin, almost imaginary seam between your palm and the material in the first fraction of a second of contact. And this is the number that governs the sensation your nerves report as sudden coldness or sudden warmth, because your nerve endings are stationed right there, at the seam, not deeper in the material, and not deep in your own hand either. Metal has high effusivity, not simply because it conducts heat well, but because that conductivity is joined by a respectable density and a workable heat capacity, and the combination means that when your warm hand meets a cool metal surface, the boundary temperature that both surfaces are forced to agree upon lands much closer to the metal's original cool temperature than to your hands. The metal, thermally speaking, barely budges to meet you partway, and so your skin, which was expecting the gentler warmth of your own hand's radius, suddenly finds itself in contact with something stubbornly close to shelf temperature, and the nerves fire accordingly, urgently,
as though something significant has happened, which, from their narrow point of view, it has. Wood, despite having a heat capacity that is not so very different from many everyday materials, is held back by its poor conductivity, and that poor conductivity drags its overall effusivity down considerably, even though on its own, heat capacity might have suggested wood could hold its ground. The practical result is that the boundary temperature where wood meets skin settles much closer to your hand's temperature than to the wood's original coolness, because the wood simply cannot supply cold fast enough to keep dragging that shared boundary down. It concedes the meeting point almost as soon as contact is made. Your nerves, sensing a boundary that has barely moved from your own skin's temperature, report something mild, unremarkable, hardly worth waking up for, so to speak, and this is why the wood feels, quite honestly, close to room temperature, even though a thermometer would have told you, if you'd bothered to check beforehand, that wood and metal were exactly, precisely, the same.
It's worth pausing on the fact that effusivity is doing something different from what conductivity alone was doing in our earlier discussion. Conductivity told us how fast heat moves once it's already flowing, the rate of that ongoing transfer we discussed a few minutes ago, the electron sea hauling energy away at its brisk, sustained pace. Effusivity tells us something that happens even before flow properly establishes itself, the instantaneous compromise reached at the interface, the number that decides how the very first impression is going to feel. They're related, certainly, cousins in the same family of properties, both descended from conductivity in some sense, but they are not identical twins, and a material could, in principle, have unusual conductivity and unusual heat capacity in such a way that its effusivity behaved a little differently than conductivity alone would have predicted, though for the ordinary materials in your bedroom, metal and wood and stone and fabric, the two properties tend to point in the same general direction, which is part of why they've been easy to conflate. There's yet another property worth naming gently before we move on, not to overload the evening with vocabulary, but because it explains something about duration rather than just first contact, and that property is thermal diffusivity, a term that sounds almost like effusivity, but measures something else again, namely, how quickly a temperature change, once it begins, spreads through a material's interior, how fast a patch of warmth or coolness travels from where it started to the regions around it. Diffusivity is conductivity divided by the product of density and heat capacity rather than multiplied and rooted the way effusivity was built, and this small mathematical difference in how the same three ingredients get combined produces two quite distinct pieces of information. High diffusivity means a temperature disturbance races through a material quickly, evening itself out, which is part of why the metal's whole mass can help absorb heat from your hand almost as one unit, keeping that hungry surface cool for a long stretch of contact. Low diffusivity means a disturbance stays local, lingering right where it started, which is part of why the small patch of wood beneath your palm warms up on its own, isolated, essentially unassisted by the wood further away, which barely notices anything has happened at all. So we now have several related but distinct characters in this quiet drama. Conductivity, governing the ongoing rate of flow. Effusivity, governing the shared temperature, struck the instant two surfaces meet. Diffusivity, governing how quickly that disturbance travels onward through the material once it's underway, and behind all three, density and heat capacity, doing their own separate work, shaping how much a material can carry and how readily it gives that capacity up. None of these properties contradicts any of the others. They aren't competing theories about what's really happening.
They're different angles of measurement on the same underlying physical situation. The way a single conversation might be described accurately in terms of its volume, its pace, and its emotional tone. Three separate observations about one shared event, each true, each incomplete without the others.
And it's this last idea, the incompleteness of any single measurement taken alone, that leads us back, gently, to the nerves themselves. Because if effusivity determines the boundary temperature your skin actually meets, then the sensation you experience isn't a direct readout of that boundary temperature either. Not exactly. Not the way a thermometer's readout is a direct readout of the mercury's height. Your nerve endings are translating something, converting a physical event into an electrical signal your brain will later interpret as an adjective, cold, or cool, or merely present, and that translation step turns out to have its own curious rules that have less to do with temperature itself than with the rate at which temperature is changing, which is a rather different thing to measure, and a rather different thing to explain, and exactly where this story is headed next, once you're ready to follow it there. Let your hand settle, just for a moment, onto whatever is nearest you right now, and picture, without needing to actually do it, the very first fraction of a second after skin meets surface. Before any of this becomes a feeling you'd bother naming, it's already a small negotiation happening between two very different territories. One of them is your skin, which is not a simple thing at all, not a passive wrapper, but a living, layered, richly wired surface, warmed from below by a steady traffic of blood moving through vessels that are, at this very moment, adjusting their own diameter slightly, without asking your permission, in response to the room's temperature and your own state of relaxation. The other territory is whatever material you've touched, which has no blood, no adjustment, no interior warmth being pumped in from anywhere, only whatever heat happened to already be sitting inside it, arranged the way its own conductivity and effusivity allow. Skin, it turns out, runs a mild, low-grade thermal economy of its own, and this matters more than it might seem to at first. The surface of your palm, right now, is probably sitting somewhere between 30 and 34 degrees Celsius, depending on the room, your circulation, whether you've just come in from outside, whether you're anxious or drowsy or somewhere in between. And this number isn't fixed the way a thermostat setting is fixed. It drifts. Cold rooms pull it down as blood vessels near the surface narrow, sending less warm blood to the extremities and keeping more of it circulating closer to the body's core, an old strategy for conserving heat that your body still performs automatically, without any instruction from you, the way it did for every hand that ever reached for a stone tool or a clay cup or a cold well bucket handle in the dark. Warm rooms, or a flushed, relaxed state, let those vessels open a little, and more blood moves closer to the skin, carrying its warmth outward, so the same palm on the same evening can present a slightly different starting temperature, depending on what's been happening to the body attached to it. This matters because effusivity, that quantity from a few moments ago, that decides the shared boundary temperature the instant two surfaces meet, only knows what to do with the numbers it's given, and one of those numbers is your own skin's temperature at that exact second. A slightly warmer hand, meeting a slightly cool piece of wood, strikes a slightly different bargain than a slightly cooler hand, meeting the same piece of wood. The material hasn't changed. You have. This is part of why the same tabletop can feel very faintly different to the same person on different evenings, or why one hand, having just been tucked under a blanket, can register a surface as cooler than the other hand, which has been resting in open air.
Neither reading is wrong. They're both accurate accounts of two genuinely different meetings between skin and surface, because the skin itself walked in carrying a different starting condition. Then there's moisture, which tends to get overlooked, though it shouldn't be, because damp skin behaves rather differently against a cool surface than dry skin does. A faint film of moisture on the palm, whether from humidity in the room or the ordinary, barely noticeable dampness skin carries most of the time, changes the effective contact between fingertip and material, partly because water itself is a fairly good conductor of heat compared to the outer layer of skin, and partly because that thin layer can slightly improve how completely the surface and the skin are actually touching one another, filling in some of the microscopic gaps that would otherwise be sitting there, full of still, insulating air. A perfectly dry fingertip pressed to metal, and a faintly damp one pressed to the same metal, are not having quite the identical conversation with it, even if the metal itself hasn't changed in any way at all. And this brings us naturally to pressure, and to contact area, two things that sound almost too obvious to mention, and yet quietly shape everything. Skin is soft. It yields. Press a fingertip gently against a plank of wood, and only a small, shallow patch actually makes contact, because wood, especially something like pine or cedar, has enough natural texture, enough microscopic hills and valleys left over from its grain, that only the high points truly touch you, while tiny pockets of trapped air sit in between, and air, as we've already spent some time appreciating, is a poor conductor, so those pockets act as a whisper of insulation, a series of miniature buffers scattered across the point of contact. Press harder, and the skin deforms a little more, flattening itself into some of those valleys, increasing the true contact area, which allows a bit more heat to leave through a bit more surface, which is part of why pressing firmly against something can make it feel very slightly cooler than merely resting a hand upon it. The material's temperature hasn't moved, only the geometry of your hand's surrender to its shape has. Metal complicates this in an interesting way, because a machined or polished piece of metal, a doorknob, a railing, a spoon, tends to have a far smoother surface than wood, at the microscopic scale, fewer valleys, fewer trapped air pockets, a surface that skin can meet almost completely on first contact, without much need to deform or press harder to improve things.
This is one more quiet reason metal often announces itself so immediately and so fully, not only because of what conductivity and effusivity are doing beneath the surface, but because the geometry of contact itself is more complete, more total, from the very first instant, leaving very little of that soft, gradual settling in that a coarser, more textured material invites. But perhaps the most interesting part of this early moment isn't any single one of these factors on its own, it's that they're all happening together, at once, in the same brief span of time, layered on top of each other, so that what you actually feel is never a clean, isolated readout of temperature, or of conductivity, or of moisture, but some blended, momentary sum of all of it, arriving at your nerve endings as a single, wordless impression, before your mind has done any interpreting at all, and even this blended impression doesn't sit still. It shifts, gently, the longer the hand stays in place, because the small patch of skin in contact with the material is cooling, however slightly, as heat leaves it, and the material just beneath that patch is warming, however slightly, as heat arrives, and these two small, local, opposing drifts continue, for as long as contact is maintained, drawing closer and closer to some shared value they'll never quite fully reach, not within any span of time you'd wait around for. This is why a hand, resting on a cold metal surface for several seconds, often reports a slightly different, slightly gentler sensation than the very first fraction of a second did, why the initial shock softens, not because the metal has changed its mind about anything,
but because the skin's own local patch has been quietly cooled by the ongoing exchange, narrowing the gap between the two temperatures meeting there, easing the rate of transfer as it goes, the way a fast conversation naturally slows once both sides have said the more urgent things they had to say. Blood flow beneath the skin plays its part here too, working, in its slow, unhurried way, to resupply that cooling patch with a little more warmth from deeper tissue, a modest but continuous effort to hold the local temperature from falling as far as it otherwise might, an effort that can noticeably change how a prolonged touch feels compared to a brief one. All of which suggests that the sensation you're following, right now, in your own imagined hand resting on your own imagined surface, was never a single fixed fact waiting to be read off, but something closer to a conversation continuing quietly over time, shifting in small increments as skin and material adjust to one another. And it's this shifting, this rate of change happening moment to moment, that the nerves themselves seem to care about most of all, far more, it turns out, than they care about the plain static number a thermometer would give you if you asked it to simply describe how cold something is.
Let your attention drift, if it wants to, toward a bedroom floor on a cool morning, the kind of floor that has two different materials meeting at some threshold, tile in the bathroom, carpet in the hallway, and the strange small discovery a bare foot makes crossing from one to the other, a discovery so ordinary that most people stopped noticing it decades ago, somewhere back in childhood, when the difference between tile and carpet was still worth commenting on out loud. The tile and the carpet, if you left them both alone all night, would settle to the very same temperature, the temperature of the room itself, because air moves through both of them, however slowly, carrying warmth away from whichever surface holds more of it, until neither holds any extra at all. A thermometer laid flat against the tile, and then against the carpet, would report the same number, give or take a fraction too small to matter, and if thermometers were the only judges available, the foot crossing that threshold would have nothing to remark on. But the foot is not a thermometer, and what it notices, what it has always noticed, long before anyone had a word like conductivity to explain it, is not the temperature of the material, but the eagerness of the material, the sheer willingness of it to pull heat away from skin the moment contact begins. Tile is dense, and its particles sit close together, close enough that a little thermal energy can hop from one to the next without much hesitation, the way a roomer moves quickly through a crowded room where everyone is standing shoulder to shoulder. Carpet is mostly air, trapped in small pockets between fibers, and air is a reluctant carrier of heat, content to sit still and hold whatever warmth happens to already be near it, rather than pass it briskly along. So the bare foot on tile loses heat quickly, and the nerves, tuned as they are to the rate of that loss, rather than to any final number, report cold, sometimes sharply so, while the same foot on carpet loses heat far more slowly, and reports something closer to neutral, even though, again, if you waited long enough, both surfaces would prove to be sitting at the identical room temperature the whole time. A bed frame tells a similar story, and it's worth sitting with for a moment, since so many people have lain awake at one time or another, running a hand along the frame of their own bed without quite thinking through why one part feels different from another. A metal bed frame, the kind with cool tubular rails and a wooden headboard attached to it, have shared the same room, the same air, the same hours of overnight stillness, long enough that any difference in their actual temperature would have long since disappeared. And yet the hand, moving from the wood to the metal, registers a shift, an unmistakable one, cooler, more assertive,
faster to make its presence known. Wood, like carpet, is riddled with tiny air-filled spaces left behind by the tree's own long-ago plumbing, the vessels that once carried water and nutrients up through the trunk, now empty, now serving no purpose except to slow the passage of heat through the timber. Metal has no such spaces. Its structure is a dense lattice, and beyond that, it carries a second advantage in this particular contest, since many metals are also full of loosely bound electrons, drifting through the material with a certain freedom, and these same electrons that make metal an excellent conductor of electricity also make it an excellent conductor of heat, ferrying thermal energy away from the warm hand with unusual speed.
So the headboard, resting at exactly the temperature of the rails beside it, feels warmer simply because it is slower to act on that temperature, slower to draw heat away, and the rails feel colder for the mirror image reason, not because they are colder, but because they are quicker. Stone countertops belong to this same family of experience, and anyone who has ever pressed a palm flat against a kitchen counter first thing in the morning, before the day's cooking has warmed the kitchen at all, will recognize the particular chill of granite or marble, a chill that can feel almost damp in character, even though the stone is perfectly dry. Stone shares tile's density, that close-packed arrangement of particles that lets heat move through it briskly, and so it draws warmth from the hand at a rate the nerves interpret as cold, sometimes quite convincingly so, even on a stone slab that a thermometer would insist is sitting at the very same 70 degrees as the wooden cutting board resting 6 inches away on the very same counter. It's worth noticing, too, that some counters are chosen precisely for this quality, prized by cooks for centuries for their steadiness under a hot pan or a rolling pin, since a material that moves heat quickly away from a warm object will also, by the same logic, moderate temperature swings on its surface with a kind of practical calm. Foam and fabric sit near the opposite end of this spectrum from stone and metal, and this is no accident, since so much of what foam and fabric are built to do involves trapping air rather than letting anything move freely through them. A foam pillow, a fleece blanket, a plush upholstered chair, all of these hold pocket after pocket of still air within their structure, and still air, as it turns out, is one of the more reluctant substances in the ordinary world when it comes to carrying heat from one place to another. This is precisely why these materials feel warm to the touch even when they are not, in any active sense, warm at all. And it's also why they make such effective insulation once a body has settled into them and begun, slowly, to warm the trapped air nearby, air that then has nowhere much to go and no eager pathway for carrying that warmth away again. Plastics fall somewhere in the middle of all this, neither as reluctant as foam, nor as eager as metal, and this middling quality is itself worth a moment's notice, since plastic is so often chosen by designers for exactly this reason, for handles and casings and the outer shells of countless ordinary objects, precisely because it neither shocks the hand with sudden cold, nor holds heat in some worrying way. Glass tends to sit closer to stone and tile on this same spectrum, dense and orderly in its structure, more willing than plastic to draw heat from a resting hand, which is part of why a glass tabletop or a glass shower door so often reads as cooler than the wood or tile surrounding it, even in a room where every surface has had all night to arrive at the very same shared temperature. And there is one more comparison worth pausing over before this particular thread closes, a comparison that puzzles people more than almost any other once they start thinking about it carefully,
And that's the strange difference between room temperature air and room temperature water. Step into a swimming pool that has been sitting, by every measurement, at precisely the same 78 degrees as the air around it, and the water will feel unmistakably cooler the moment it closes over skin, cooler in a way that seems almost to contradict the thermometer sitting poolside, insisting both readings match. The explanation, once again, has nothing to do with any hidden difference in temperature, and everything to do with density, since water molecules are packed vastly more closely together than air molecules ever are, close enough that heat can move from skin into water far more efficiently than it can move from skin into air, and closely packed water also carries away far more heat per unit of contact simply because there's so much more material touching the skin at once, molecule pressed against molecule, in a way that loose, sparse air never quite manages. This is the same underlying idea that has been circling through every example so far: tile and carpet, metal and wood, stone and foam, glass and plastic, applied now to something as ordinary and as easily overlooked as stepping from a warm room into a warm pool and noticing, with a small flicker of surprise, that warm didn't feel the way the number promised it would. It leads, naturally enough, to a question worth turning over slowly before sleep pulls the thread away entirely, a question about why the body seems to trust its skin's sense of speed over its skin's sense of scale, and what that trust might have once been useful for.
Now let's turn the whole idea around and look at it from the other direction, because everything said so far about coldness applies with almost eerie symmetry to heat, and the symmetry is worth sitting with for a while, quietly, before moving on to anything else. Picture a kitchen, any kitchen, on any ordinary evening. A pot has been sitting on a stove for 20 minutes, and the metal handle and the stove's cast iron grates have both been soaking in the same rising warmth the whole time, both resting in the same air, both exposed to the same low blue flame, or the same glowing coil beneath them. If someone were foolish enough to touch the bare metal handle of that pot, the burn would be immediate and severe, far more sudden and far more damaging than touching, say, the wooden spoon resting beside it on the counter, even though the wooden spoon has been sitting in that same warm kitchen air for just as long, and may in fact, if it was resting near the stove, have absorbed nearly as much ambient heat. The metal feels catastrophically hot. The wood feels merely warm, comfortable even, safe enough to pick up without thinking twice. And the reason is the very same reason that made the metal railing feel so much colder than the wooden banister on a winter morning, the very same conductivity that was doing all the work in every cold example so far, only now running in the opposite direction, carrying heat toward the skin instead of away from it, and carrying it just as efficiently, just as fast, with just as little regard for comfort. This is worth pausing on, because it can seem, on first hearing, like some kind of contradiction. How can the same property make metal feel unusually cold in one setting and unusually hot in another? But there's no contradiction at all once the mechanism is remembered clearly. Metal's high thermal conductivity doesn't have any built-in preference for warming or cooling. It doesn't care which direction the heat happens to be moving. It only cares about how quickly heat moves, how efficiently it can be conducted from one material into another, following whatever temperature difference happens to exist between them. When metal is colder than skin, that efficient conduction pulls heat rapidly out of the fingertips, and the nerves report a sharp, fast chill. When metal is hotter than skin, that same efficient conduction
pushes heat rapidly into the fingertips, and the nerves report a sharp, fast burn.
The metal is, in both cases, simply doing what metal does, moving thermal energy across its surface as fast as physics will allow, indifferent to whether that motion happens to feel pleasant or painful to the person on the other side of the contact. Wood, meanwhile, keeps doing what wood does, regardless of which direction the temperature gradient runs. Its cellular structure, full of tiny air pockets trapped between fibers that were once living plant tissue, slows heat flow no matter which way that flow is trying to go. A warm wooden spoon releases its heat into a hand slowly, gently, the way it would have absorbed cold slowly and gently on a winter morning. A hot wooden spoon handle, similarly, releases its stored heat gradually enough that a hand can usually make contact and adjust before any damage is done, whereas a metal spoon handle, left resting in the same simmering pot, would already be dangerously hot within moments, heat traveling up through the metal from the submerged bowl of the spoon to the handle a person is about to grasp, sometimes faster than anyone standing at the stove would expect. This is precisely why cookware handles are so often made from something other than the metal used for the pot or pan itself. Wooden handles, handles wrapped in silicone, handles fitted with a plastic sleeve, handles built around a hollow chamber of trapped air, all of these solve the very same problem, which is that a metal handle would transmit the heat of the cooking surface directly and rapidly into a human hand, often before the hand's owner had time to register what was happening. Historically, this was solved with cloth, thick woven potholders, and folded towels used for centuries before anyone had a name for thermal conductivity, cooks reaching instinctively for fabric because fabric, like wood, is riddled with trapped air and simply refuses to move heat quickly. Cast iron skillets, beloved for how evenly and thoroughly they hold and radiate heat once they're hot, are for that very same reason notoriously dangerous to grab by their metal handles, which is why so many cast iron pans today are manufactured with a small loop of silicone or a wrapped cloth sleeve sold separately, sometimes with a handle shaped from an entirely different material bonded to the metal body. Even the design of an old-fashioned soldering iron, or a fireplace poker, or a blacksmith's tongs, reflects the same very old, very practical understanding. Insulated grips at one end, conductive metal doing the work at the other, the two materials chosen specifically because they behave so differently when heat starts moving through them. There is something almost poetic in realizing that the coldness of a doorknob on a January morning and the danger of a skillet handle on a stovetop are, at bottom, expressions of the same physical fact, just pointed in opposite directions. Both are stories about how readily a material lets heat pass through it, about the speed of transfer rather than the amount of heat present. A pot handle at 140 degrees can injure skin in a way that a sauna at 140 degrees generally does not, because the pot, being metal, conducts that heat directly and completely into the hand almost instantly, while the air of a sauna, being sparse and full of empty space between its molecules, delivers that same nominal temperature far more gently, a slow simmer rather than a sudden scald, this being the same low-density story that explained why warm air never quite matches the felt intensity of warm water. Skin doesn't have a thermometer. It has something closer to a rate detector, a way of sensing how fast energy is arriving or departing, and it interprets that rate as an estimate of danger or comfort,
an estimate that is usually useful and occasionally, as with the pot handle, dramatically necessary for survival. It's worth noticing, too, that this reversal explains something people often observe but rarely articulate about touching metal outdoors in full sun during summer. A metal playground slide, a car's seatbelt buckle, a metal fence rail, all can become shockingly hot after even a modest stretch of direct sunlight, hot enough to genuinely burn skin, while a nearby wooden bench or a stretch of rubberized track surface sitting under the very same sun for the very same length of time might feel only pleasantly warm to the touch. The sunlight delivers energy to both surfaces at more or less the same rate, but the metal, once it absorbs that energy, conducts it so efficiently that its whole structure heats rapidly and evenly, and then delivers that stored heat straight into any skin that touches it, all at once, all in a rush. Wood and rubber, holding on to their trapped air, warm more slowly, store less heat near the surface, and, crucially, release it into skin far more gradually, giving the nerves time to register mild warmth rather than sudden pain. This is why parents so often warn children away from metal playground equipment on hot afternoons, an old and practical piece of folk wisdom that turns out to rest on exactly the same physics as the difference between a stone floor and a wool rug. So the metal is never actually the villain in either story, cold morning or hot stovetop, and it was never actually the culprit that popular imagination sometimes makes it out to be. It is simply a material that conducts heat with unusual efficiency, an efficient messenger rather than a source, carrying energy wherever a temperature difference invites it to travel, whether that means draining warmth from a hand at dawn or delivering warmth into a hand at dusk.
And once this reversal settles into place, once it becomes clear that the very same property producing that startling winter chill is also producing that summer burn, a new and gentler question starts to surface, one about why human skin evolved to care so intensely about the speed of a sensation and comparatively so little about its total scale, and what, deep in some distant evolutionary morning, that particular kind of attentiveness might once have helped a person survive. Let's slow down here and follow that question inward, into the skin itself, because the answer has less to do with heat and cold as physical quantities, and more to do with the particular kind of instrument the body uses to notice them. Human skin does not contain a single thermometer. It contains two separate populations of nerve endings, and they do not agree with each other, not exactly, and that disagreement turns out to be doing quiet, important work. One population, the cold receptors, sits just beneath the surface of the skin, closer to the world outside, and it fires most vigorously when temperature drops, particularly when it drops quickly. The other population, the warm receptors, sits a little deeper, and it responds to rising temperature, though it is fewer in number and, by most estimates, slower and less densely distributed across the body than its cold-sensing counterpart. This asymmetry alone explains a great deal. A hand has far more machinery devoted to detecting cold arriving quickly than it has devoted to detecting warmth arriving quickly, which means the nervous system is, in a sense, built with a bias, tuned by some long evolutionary process to treat sudden chilling as the more urgent category of news. But the deeper strangeness lies not in how many receptors there are, but in how they behave the moment contact begins. Touch a piece of metal, and the cold receptors beneath that patch of skin do not simply settle into a steady rate of firing that matches the object's actual temperature. They spike, they fire, in a rapid burst, right at the instant of contact, a kind of alarm rather than a report, and only afterward do they settle down into a calmer, more measured rhythm that better reflects the true, stable temperature of what is being touched. This burst is called a transient response, and it exists because the nervous system, at least in this particular circuit, seems to care enormously about the rate of change and only secondarily about the final resting value. A slow, gradual cooling, the kind that happens when a room loses heat overnight, produces almost no such spike. A sudden cooling, the kind that happens when fingertips meet a metal railing, produces a sharp one. The metal is not colder because it is metal. It is registered as more urgently cold because it delivers its coldness so quickly that the receptors interpret the speed itself as information worth shouting about. This is worth sitting with for a moment. In the unhurried way one might sit with any small, well-made mechanism, because it explains something that otherwise seems paradoxical. If two objects are genuinely at the same temperature, and both are markedly cooler than skin, a person's nervous system does not report them as equally cold at first contact, even though, given enough time, it eventually will. The first touch is dominated by the transient spike, and the size of that spike is shaped by how fast heat is actually leaving the skin, not by the object's temperature read off some external scale. A dense, conductive object pulls heat away fast, so its spike is large. A less conductive one pulls heat away slowly, so its spike is smaller, more muted, easier to overlook. Two surfaces sitting at the identical, coldly indifferent number on a thermometer can therefore produce entirely different first impressions in a human hand, not because the hand is being fooled, but because the hand, quite reasonably, is measuring something else entirely, the rate at which its own warmth is being drawn away, moment by moment. Then comes a second phenomenon, one that plays out a little more slowly, and is, in its own way, just as remarkable. It is called adaptation. Hold a hand against that same piece of metal for a while, and the sharp, urgent quality of the sensation begins to fade, even though the metal has not changed and the hand has not moved. The receptors, having delivered their initial burst of information, gradually quiet down, firing less and less as the seconds pass, not because the cold has weakened, but because the nervous system has, in effect, already filed its report and moved on to watching for new developments rather than continuing to narrate the old ones. This is the same general principle that lets a person stop noticing the collar of a shirt against their neck within a minute of putting it on, or stop smelling their own kitchen after they have stood in it for a quarter of an hour. Sensory systems, quite broadly across the body, are built to notice change and to grow quieter in the presence of the unchanging, conserving attention for whatever might be new, whatever might still require a decision. Adaptation is part of why the coldest sensation from touching metal often arrives at the very instant of contact, and then eases, even if only slightly, even while the hand remains pressed against the same cold surface. It is also part of why the transition matters so much. Pull the hand away and set it back down again, even on the exact same spot of the exact same metal railing, and the transient spike returns almost as sharply as before, because the receptors are, in a real sense, encountering the change anew. The nervous system is not keeping a running tally of absolute coldness so much as continually asking a narrower,
more urgent question: is the situation changing right now, and if so, how fast, and in which direction? Metal is unusually good at making that question answerable in a hurry, which is precisely why it so reliably produces the sharpest, most attention-grabbing version of the sensation. There is a further layer to this, gentler and more psychological, though no less rooted in real physiology, and it involves what a hand has touched just before. If a hand has just come from something quite warm, a mug of tea, a car heater vent, a patch of sunlit fabric, and then moves to touch a piece of metal sitting at ordinary room temperature, that metal will feel considerably colder than it would have felt if the hand had come instead from something already cool. This is not imagination, and it is not a trick of the mind layered over some separate, more honest physical truth. The receptors themselves are responding to a relative shift, to the size and speed of the drop in temperature they are experiencing, and a hand arriving from warmth experiences a larger, faster drop than a hand arriving from cold, even when the metal itself has not changed in the slightest. Expectation plays a role here too, though a more modest one than people sometimes assume. A person who has been told, correctly or not, that a surface will feel icy tends to flinch a little harder at first contact, tends to interpret an ambiguous signal in the direction they were primed toward.
But this effect layers on top of the physical transient response rather than replacing it, a kind of interpretive shading applied to a signal that was already, at its root, a faithful report of something real happening in the skin. None of this makes the sensation any less trustworthy, only more particular in what it is actually measuring. A cold receptor does not measure absolute temperature the way a thermometer does, patiently and impartially, indifferent to history and context. It measures a rate, a direction, a departure from whatever the skin had grown used to a moment before, and it reports that departure with an urgency calibrated, it seems, by millions of years of a nervous system that needed to know quickly whenever conditions were shifting in a way that might matter, long before it needed to know precisely by how many degrees. A campfire cooling toward morning, a stream crossed at dusk, a stone cave wall in early spring, these were the kinds of encounters that shaped the instrument long before anyone had smelted a single piece of ore or forged a single railing, and the instrument, remarkably, has changed very little since. And once the transient spike, and the slow settling of adaptation, and the quiet influence of what a hand touched a moment earlier, are all laid out side by side, a further, and perhaps even homier question begins to take shape, one that turns away from the hand for a moment, and looks instead toward the feet, and toward the particular, familiar chill of a bathroom floor early on a winter morning, when tile and wood sit only a few steps apart, and somehow feel like they belong to entirely different seasons. It's worth pausing on how anyone came to measure any of this precisely in the first place, because for most of human history, there was simply no instrument that could settle an argument between two people who each swore, with total sincerity, that a stone floor was colder than a wooden one when both had supposedly been sitting in the same room all night. The hand was the only tool available, and the hand, as we've seen, lies in its own particular, honest way. What was missing was something that could report temperature without the confounding rush of thermal transfer, something that would simply sit and register a state rather than a rate. That something arrived slowly and in pieces, and the people who built it were not thinking about bathroom floors at all. The early thermoscopes of the late 1500s, the sort of open-air devices tinkered with in workshops across Italy, used the expansion and contraction of air or liquid in a glass bulb to show that something was changing, without offering any fixed scale to say by how much. It was a start, but only a start, because a device that shows change without a number is really just a more honest hand, still relative, still innocent of the idea that there might be an absolute 0 point or an agreed-upon degree. The scale had to be invented separately from the sensing, and this took another century and a half of arguing, largely because everyone had a different idea of what should count as a fixed reference point. Some used the temperature of a cellar. Some used the melting point of butter, which, if you think about it for a moment, is a wonderfully specific and wonderfully unreliable thing to standardize against, since butter is not one substance but a mixture, and melts across a range rather than at a single crisp threshold. It was only with Daniel Fahrenheit's mercury thermometer in the early 1700s, and shortly after, with Anders Celsius proposing his own scale, anchored to the freezing and boiling points of water, that temperature became something portable, something two people in two different cities could compare and trust to mean the same thing. But even a good thermometer, sitting quietly against a piece of metal and a piece of wood, will eventually tell you the same story for both, because given enough time, they do reach the same temperature, the temperature of the room around them. The thermometer, patient and unhurried, is not fooled by the early transient the way a fingertip is. So a thermometer alone actually solves the wrong problem. It confirms that the materials are equally warm in the sense that matters to a physicist, without explaining why they feel so different to a hand, which is really the sense that matters to anyone standing barefoot at 6 in the morning. What was needed was not a better thermometer, but an entirely different kind of question. A question not about temperature itself, but about the willingness of a material to let heat move through it. And that question did not really get asked properly in the language physics could use until the early 1800s, in France, by a man who spent an unusual amount of his working life thinking about heat moving through solid objects because he happened to also be thinking, obsessively, about Egypt. Jean-Baptiste Joseph Fourier had traveled with Napoleon's expedition to Egypt as a young man, and by most accounts, he came back from that experience with a fixation on heat that bordered on the eccentric, reportedly keeping his wounds uncomfortably warm for the rest of his life, and wrapping himself in heavy layers, even in mild weather, convinced that the deserts had shown him something true about the human relationship with temperature. Whatever the psychological roots of that fixation, it pointed him toward one of the more elegant pieces of mathematical physics ever produced, a formal description of how heat spreads through a solid body over time, driven not by some vague notion of hot and cold trading places, but by a clean, quantifiable relationship between temperature gradients and the flow of energy. Fourier's law, as it came to be called, said essentially that heat flows from warmer regions to cooler ones at a rate proportional to how steep the temperature difference is and to a property of the material itself, a number that came to be known as thermal conductivity. Different materials, Fourier's framework made clear, could sit at exactly the same temperature and still behave completely differently the moment heat was asked to move through them, some conducting eagerly, some resisting, some acting almost like heat wanted to stay put. This was, in a real sense, the first rigorous language available for the very question a bare foot had been asking on a cold floor for as long as there had been bare feet and cold floors, though it would take another century before anyone thought to measure that property directly and reliably enough to compare materials with real confidence. The instrument that eventually did this, called the guarded hot plate, is unglamorous in a way that suits its purpose. Picture a slab of the material to be tested, sandwiched between a heated plate on one side and a cooled plate on the other, with a steady, carefully measured flow of heat pushed through it from hot to cold. The clever part, the part that gives the device its name, is the guard, a ring of additional heated material surrounding the central heater, kept at exactly the same temperature so that no heat can sneak sideways and escape before making its official, measured journey straight through the sample. Engineers refined this apparatus through the early and middle 20th century, chasing ever more precise measurements for reasons that were rarely about comfort and much more often about industry, about insulating buildings efficiently, about designing better refrigerators, about knowing exactly how much energy a given wall or pipe or oven door would lose over the course of a winter. Wood, tested this way, might show a thermal conductivity of something like 1/10 of a watt per meter per degree, a small, unhurried number. Aluminum, tested the same way, might come in at over 200, and steel somewhere in between, but still enormously higher than wood. Numbers that, once measured this precisely, finally gave a rigorous, repeatable backbone to what fingers had been reporting all along, in their own imprecise but not incorrect language. Around the same period, a separate but related technology was quietly developing, one aimed not at measuring a single number for a single sample, but at watching heat move across a surface in real time, visibly, as an image rather than a figure on a page. Infrared imaging traces its practical roots partly to military and reconnaissance work in the mid-20th century, where the ability to detect the faint heat signature of an engine or a person in darkness carried obvious value and only later drifted into civilian and scientific use, into building inspections, into medical diagnostics, into the kind of demonstration a teacher might run for a room full of students, holding a thermal camera up to a hand pressed against a table so that everyone can watch, in false color, the warm print of the palm bleed instantly outward into the surrounding wood, staying vivid and slow to fade, compared to how quickly that same warm print would vanish, swallowed almost immediately on a sheet of aluminum. The camera does not measure anything Fourier's equations did not already predict, but it does something the equations alone cannot, which is make the invisible plainly visible, turning an abstract property into a picture anyone can read at a glance, a orange smudge, cooling stubbornly against dark wood, a flash of color extinguished almost instantly against pale metal. Modern materials testing has only extended this lineage further, refining old methods and adding new ones. Laser flash analysis, for instance, where a brief pulse of energy is fired at one face of a thin sample, and sensors on the opposite face time exactly how long it takes for that pulse of warmth to arrive, a technique fast enough and precise enough to characterize materials that would have taken a guarded hot plate hours or days to assess properly. None of this newer, faster instrumentation overturned what Fourier worked out with pen and paper in the early 1800s. It has mostly just made his ideas easier to apply quickly across a wider range of materials for engineers designing everything from spacecraft heat shields to the soles of hiking boots. And all of it, the mercury thermometers and the guarded plates and the false color cameras and the laser pulses, exists to answer, with increasing precision, the very same question a bare foot on a cold morning
has always been asking without any instruments at all, a question that leads naturally back to that floor, and to why tile and wood, sitting side by side in the same quiet room, can feel like they belong to two entirely different mornings.
Let's settle a few things that tend to get tangled together somewhere around this point in the night. Quiet misunderstandings that feel true because they match the feeling in your hand, even though the feeling in your hand is not, in this one narrow sense, entirely trustworthy. The first tangle is the idea that metal is simply colder than wood, as a fact about the metal itself, sitting there in your kitchen at midnight, being colder the way it might be heavier or shinier. It is not. Not indoors, not in a room that has had all afternoon and evening to settle into a single steady temperature. Every object in that room, the countertop, the cutting board, the cast iron pan hanging by the stove, the wooden spoon resting beside it, has been quietly equilibrating with the air around it for hours, trading warmth back and forth in both directions until there is no net trade left to make. Given enough time and no outside interference, they all arrive at the same temperature as the room, because that is simply what happens when things are left alone together long enough. A thermometer laid against the pan and then against the spoon would report the same number, or close enough that the tiny difference would not matter to anyone. The metal is not secretly cooler, it only behaves, the instant your hand arrives, as though it were. This is where the second tangle sits, waiting, which is the belief that the shine has something to do with it, that a polished surface feels cold because polish itself is cold, the way a matte surface might feel warm out of some inherent softness. It is an understandable guess. Shiny things do tend to be metal, and metal does tend to feel cold, so the mind links the two, shine and chill, the way it links smoke and fire, even though one does not cause the other. But polish a piece of wood until it gleams, and it will still feel far warmer to the touch than a dull, unpolished slab of steel sitting right beside it. Sand a piece of metal until it is matte and rough, and it will still pull heat from your palm at nearly the same alarming rate it did when it gleamed. The shine is a fact about how the surface reflects light. It has nothing to do with how the surface conducts heat, and the two properties, optical and thermal, happen to travel together in metals for reasons of atomic structure, but they are not the same property wearing two different coats. The third tangle runs deeper, and it is worth sitting with for a moment because it touches something almost philosophical, buried in the way we talk about temperature at all. We say a hand feels cold, as though cold were arriving, as though there were some substance, some cold stuff, flowing out of the metal and into the skin. This is an old habit of language, and an old habit of thought, too. For a long stretch of history, plenty of serious thinkers treated heat itself as a substance, something called caloric, an invisible fluid that flowed from hot things into cold things, the way water flows downhill. It was a genuinely useful idea for a while, useful enough that it helped engineers reason about steam engines with real success. But it was wrong in a specific and important way, because heat is not a substance being transferred, it is energy, the jostling motion of atoms and molecules, and what actually happens at your fingertip is not that cold flows in, but that heat flows out. There is no cold arriving from the pan. There is only warmth leaving your hand, drawn away into the metal faster than your body can replace it, and what your nerves register as the sensation of cold is really just the rate of that departure. Nothing crosses over from the metal to you except, in a sense, absence, the growing absence of the energy your hand just had a moment ago. It is a small correction, but it reshapes the whole picture,
because once cold stops being a thing that exists and starts being understood as simply less heat, or heat leaving quickly, a lot of confusing questions answer themselves. There is no cold to explain the metal having more of. There is only a rate of heat loss to explain, and that rate depends on conductivity, exactly the property we have been circling this whole evening. Which brings us to the fourth tangle, the puzzle of the disagreeing thermometer, because if metal and wood really are the same temperature, a fair question drifts up out of the dark. Why does an actual thermometer, the physical instrument, sometimes seem to hesitate, or read something slightly different, when pressed briefly against one surface and then another? The answer is not that the room lied, it is that a thermometer, like a hand, is also a physical object that has to reach thermal equilibrium with whatever it touches, and that process takes time, and different surfaces let it happen at different speeds.
A thermometer bulb pressed against wood exchanges heat slowly, because wood is a poor conductor, so if you lift it away too soon, before it has had time to fully settle, it may still be reading closer to your hand's warmth, or the room air, than to the true surface temperature. Press that same bulb against metal, and because the metal conducts so efficiently, the thermometer reaches true equilibrium almost immediately, giving you a fast, accurate number. So, a careless, too quick reading really can appear to disagree between materials, not because the materials are different temperatures, but because the instrument itself needs different amounts of patient contact time to tell the truth. Exactly the same problem your hand runs into, just measured with numbers instead of nerves. Given enough time held steady against each surface, a good thermometer will always converge on the same reading for both, confirming what waiting has already told you, that the room agrees with itself. Which leads, gently, to the last and maybe most important tangle of the evening, the idea that equal temperature should mean equal feeling, since surely, if two things are the same temperature, touching them should be the same experience. This sounds reasonable, and it is exactly the assumption that trips people up, because temperature and the sensation of touching something are not the same measurement at all. Temperature describes a static condition, a kind of average restlessness among atoms, present whether or not anyone ever touches the object. What your hand actually detects is not that static number, but a rate. Specifically, the rate at which heat is leaving your skin through contact, and that rate depends on an entirely separate property, thermal conductivity, how efficiently a material's atoms pass their jostling motion along to their neighbors. Wood and metal can share a temperature completely, down to the last fraction of a degree, and still behave in wildly different ways the moment skin meets surface, because one carries heat away at a trickle, and the other at a flood. Sameness of temperature guarantees nothing about sameness of experience. It only sets the starting line, what happens after contact, how quickly warmth drains, how sharply the nerves respond, how long the sensation lingers or fades. All of that is governed by conductivity, a completely different quantity, doing a completely different job. So none of it was ever a trick. Not the tile, not the pan, not the doorknob in the hallway. The floor was not secretly colder. The metal was not hoarding chill, the way a sponge hoards water. There was no invisible cold fluid pouring into anyone's foot in the dark. There was only heat, always heat, moving the way heat always moves, from warmer to cooler, at a pace decided entirely by what stood in its way, wood slowing that departure down to something gentle and almost gradual, metal opening a wide, fast lane for it to rush along, and a nervous system built to notice speed of loss,
rather than any fixed number on a dial. Once that is understood, the whole strange choreography of a midnight kitchen starts to feel less like a mystery and more like something almost predictable, something you could, if you wanted, begin to feel out for yourself, testing it quietly with your own palm, surface by surface, room by room.
Once you start noticing this pattern, you start seeing it everywhere. Not just in kitchens and hallways, but in the built world entirely, in the choices people have made for centuries about what to wrap around themselves and what to build their shelters from. Think of a heavy wool blanket pulled over shoulders on a cold night. Wool does not generate warmth. It has no heat of its own to offer. What it does, and does well, is trap still air within its fibers, and still air is a remarkably poor conductor, a sluggish, reluctant carrier of heat. So the warmth your body makes stays close, held there by millions of tiny pockets of air that simply refuse to hurry it away. This is the same principle, working in reverse, as the metal spoon in warm soup. A blanket is not magic. It is architecture, fiber, and air arranged so that heat, once it arrives, has nowhere fast to go. Now think of a stone farmhouse, the kind still standing in parts of rural Europe after 4 or 5 centuries. Walls sometimes 2 feet thick, cut from local rock by hands that never studied thermodynamics but understood, through generations of trial and cold winters, that thick stone kept interiors steady, cool in summer, and with the help of a hearth, tolerable in winter. Stone is a moderate conductor, slower than metal, faster than wood, but its real trick was mass. A great deal of material meant a great deal of thermal inertia, a slowness to change temperature at all, so the walls absorbed the wandering heat of the day and released it gradually through the night, evening out extremes, the way a large lake stays cooler through a hot afternoon than a small puddle ever could. The builders were not thinking about atoms passing along their jostling motion to their neighbors. They were thinking about survival, about a farmhouse that did not become an oven in July or an icebox in January. But the physics underneath their good instincts was exactly the physics we have been walking through all this time. Modern buildings chase the same goal with different materials. Fiberglass insulation, foam board, even the humble air gap left inside a double-paned window, all of it is an attempt to slow heat's departure, to put something in its path that behaves the way wood behaves against a bare foot, something with a low thermal conductivity, something that makes heat work harder to get from warm inside to cold outside, or the reverse in summer, from hot outside to cool inside. A window with a single pane of glass feels startlingly cold to stand near in winter, not because the room's air near it has dropped to some dramatic temperature, but because glass conducts heat away from a nearby body efficiently enough to be noticeable. The same fast lane the metal doorknob offered, just working through air instead of through a fingertip pressed directly to the surface. Double glazing works by trapping a thin layer of gas, sometimes plain air, sometimes something slower, like argon, between 2 panes, turning that fast lane into something closer to a wandering country road. Clothing designers have understood variations of this for a very long time, often without any formal vocabulary for what they were doing. Early mountaineers, climbing peaks in the 19th century in wool and leather, layered their garments not simply for thickness, but for the air trapped between layers, learning by cold and uncomfortable experience that several thin layers, with gaps between them, held warmth better than one thick layer alone, because each gap
was another region where heat had to slow down and negotiate its way through still air rather than rushing straight through solid material. Down feathers, still used in the best winter coats today, work by the same logic taken to an extreme, each feather a tangle of fine filaments, creating countless tiny still air chambers, an almost absurd amount of insulating volume packed into something that weighs almost nothing. It is, in its way, the opposite of a frying pan, a material chosen specifically because it resists carrying heat away from the body wrapped inside it.
Tools reveal this same principle from the maker's side, in choices made deliberately, sometimes lucky, sometimes calculated after hard lessons. A well-made kitchen knife often has a metal blade fixed into a wooden or plastic handle, and this is not simply about grip or tradition. Metal edges can be sharpened to a precision that wood cannot hold, but nobody wants to grip a metal handle for long, especially not near a hot stove, where a fully metal handle would rapidly draw heat away from cookware and just as rapidly, though in the opposite direction, become uncomfortably hot to the touch itself. Pot handles.
Kettle grips, the covered part of a saucepan, these are shaped in wood or heat-resistant plastic or wrapped in insulating material, specifically because a cook's hand needs a slow lane, not a fast one, at exactly the point where fingers must make prolonged contact. Even something as ordinary as a screwdriver, plastic, or rubber around a steel shaft reflects the same quiet decision made by designers who may never once have used the phrase thermal conductivity, but who understood, through use and complaint and refinement over generations of tool-making, which materials felt right in a working hand. The stakes rise considerably once you leave the surface of the Earth. Spacecraft engineers face an environment with almost no atmosphere to conduct or convect heat away gradually, which means heat transfer becomes dominated by radiation and by direct conduction through whatever solid materials touch each other, without air to soften anything in between. A surface in direct sunlight and vacuum can reach extraordinary temperatures, while a surface in shadow, mere inches away, can plunge to extraordinary cold, because there is no atmosphere to average things out, the way Earth's air constantly does. Spacesuits are built in careful layers, some reflective, some insulating, precisely to manage this, to keep an astronaut's body from either cooking in direct sun or freezing in shadow, sometimes both at once on different parts of the same suit. The materials chosen, the layering, the trapped gaps, all of it descends from the same basic reasoning that shaped a wool blanket or a stone farmhouse wall, just pushed to a far more unforgiving extreme, where getting the insulation wrong is not merely uncomfortable, but genuinely dangerous. And all of this, the blankets, the farmhouses, the double-paned windows, the downcoats, the wooden pot handles, the layered suits built for the vacuum of space, all of it traces back to the same handful of ideas that made a kitchen floor feel cold at midnight. Heat moves from warmer to cooler. Different materials let it move at different speeds. Living skin, built to sense change rather than to read some fixed number off a dial, interprets that speed as sensation, as temperature, as cold or warm, even when the true temperature underneath is not what the nerves are reporting at all. So picture that room again, the one this whole slow explanation began in. Quiet now, the light off, the objects within it settled into whatever temperature the air around them has settled into as well. The tile floor, the metal pan, resting on its cooling burner, the wooden cutting board leaning against the counter, the brass doorknob at the end of the hallway. Every one of them, by now, likely shares almost exactly the same temperature as the air itself, and therefore as each other, molecules in each material jostling at very nearly the same average pace. No one surface secretly colder, no one surface hoarding some invisible chill the others lack. And yet if a hand were to drift out from beneath a blanket right now, and touch each of them in turn, they would not feel the same at all. The tile would feel briskly cool, the pan, colder still, sharp and immediate. The wood would feel almost neutral, almost like nothing, barely announcing itself. The doorknob would feel coldest of all, the fastest thief of warmth in the room, not because the room disagrees with itself about temperature, but because skin was never built to measure temperature in the first place. It measures loss. It measures the rate at which its own warmth is leaving it, surface by surface, material by material, and reports that rate back as feeling. There is something quietly comforting in that. Once you sit with it for a while, the world is not full of secret temperatures hiding beneath the surface, cold pockets and warm pockets scattered without explanation. It is far simpler than that, and far steadier. One law, followed patiently by every object in every room, heat drifting always from warm to cool, never troubled, never inconsistent, only moving at whatever pace the material in its path allows. The confusion was never in the world. It was only ever in the gap between what a thermometer would say and what a nervous system, doing exactly the job it evolved to do, chooses to notice instead. And now, drifting off, hand tucked back beneath the blanket, wrapped in all that trapped impatient air, that gap can finally rest too. Rest well.